I'm going to gain voltage, or sorry, gain potential. I will have a positive voltage. Cruising along, crossing over the 4 ohm resistor. I'm going in the direction of both of my currents. If I'm going with the current, I lose potential, so minus 4B minus 4C. Coming down here, I'm going across the 5 ohm resistor in the direction of the current that I've made up, so minus 5B. Going across the 10 volt power supply, and I'm going from the negative to the positive, so I gain 10. I go across the 3 ohm resistor in the direction of my currents. And that's going to be equal to 0. So I ended up back where I started. We'll simplify that in just a moment. And for the other one, you know what? I'm going to do the right loop. Just because. I start somewhere. Doesn't matter where I start. What I'm going to do is I'm going to start here, and I'm going to go clockwise. Why not? Someone want to take a shot at it?
Yes. So we have 8 getting 8 volts, and then we're just gonna go around. So we're gonna go from the positive to the negative in the battery.
Yep.
So it's minus 10.
Yep.
Okay. And then we're in the opposite direction of the 5 ohms, so it'd be plus 5B. And then we're in the direction of the 6, so it's minus 6C. And then we're back, so equals 0.
Spot on. 10 points for Gryffindor.
I'm a Ravenclaw.
10 points for Ravenclaw. I apologize for sorting you in the wrong place. We now have 2 equations, 2 unknowns. Let's simplify it. So I'm gonna just do BC equals constant. So I got a B here, a B here, and a B here. So it's negative 4, negative 5, and negative 3, so I have negative 12B. Then I have negative 4, and negative 3, minus 7C equals, and then I've got 22 here. Bring it over to the other side, negative 22. Or you have the look of what? All right, you're good with this?
I'm confused with the right loop.
Oh, the right.
Yeah,
Okay, let's do the right.
I don't understand.
You don't understand how we got this equation? Or how Luis, you think he's just making
I
stuff
mean,
up?
I understand the route that he took, but my brain wants to do, because you circled the whole,
The whole thing?
yeah,
All right, so let's just take a moment and do that.
I'm sorry.
No, not a problem. And I will show you why the dependence there. I hope. Unless there's a Carol's error. If we did the whole loop, where do you want to start?
The same spot.
Same spot. Oh, we start at the same spot, so I go across the 8 from negative to positive. Moving along, go across the 3 ohm resistor in the direction of B and C. So minus 3B, minus 3C. Going across that 12 volt. For those who missed it, we're starting here and doing the entire loop. Going across that 12 volt and from negative to positive, so plus 12. Going across that 4 ohm, minus 4B minus 4C. Across the 6 ohm, minus 6C. And then we're back to where we started. All right, you good with that?
Yeah.
Let's simplify it. So I got minus 3, minus 4. So I have negative 7B, and then C, and C, minus 13C. And then that gives me 20 equals negative 20. Are you comfortable with that?
Yes.
We're gonna come back to it in just a moment. If I simplify this, I get 5B minus 6C equals 2. If I add these two equations together, so I'm just gonna add them straight up. I have negative 12B plus 5B, which is negative 7B. I have negative 7C minus 6C, which is minus 13C. Negative equals negative 22 plus 2, which is negative 20, which is the equation we have right over there.
Yeah.
So if I have two of them, the third one I can just either add or subtract the equations and get the third one. So I have three equations here, two unknowns, but only two of the equations are independent. I'm going to stick with those two, just because that's where we started, but it doesn't matter which two you pick. We're going to solve for an unknown. Now comes to the math. Two equations, two unknowns. Solving simultaneously, substitution. Graphic's not the simplest if you want an exact answer. Cramer's rule. Is there a preference?
Kramer's rule.
Great minds think alike. So, to solve for B, the denominator will be the same for B and C, but the denominator, I'm just going to take the coefficients there. So I have the determinant of negative 12, negative 7, 5, and negative 6. And the numerator, I just take the denominator, but replace, in this case, since it's the first variable, replace the first column with the negative 22 and 2. Negative 22, 2, negative 7, negative 6. So I got a 2 by 2 determinant. So if I multiply that diagonal right there, I get 132 minus negative 14. That's feeling right. And then down here,
Okay.
that diagonal, which is 72, minus negative 35. So 146 over 107 amperes. And not opposed to if I had made a mistake, so if I made a mistake, I would rather be corrected now than later. All right, C is going to have the same denominator, so that math is already done. The numerator, I'm now solving for the second variable over there. So I replace the second column, so I got negative 12, 5. First is the same as that. And then I put the negative 22, 2. And so I get negative 24 minus negative 110 over 107, which is 146 or 107. So 110, 110. And then we can double check our work by, well, if we want to do the last one. That at least give us some sense of confidence. It doesn't tell us if the physics we've done is correct, it tells us just the math is correct. So, presenting the answer. So now, 1, R3, R4, R5, R6, and this would be magnitude, direction. Now, even though we have a magnitude and a direction of the current, current is not a vector. Because if I have current flowing in, this is the reason, the justification for it not being a vector. If I have current flowing into that junction right there, flowing into from the right, so it's flowing, sorry, coming from the left, flowing right. I have current flowing there, and then I have current flowing down. If it were a vector, there could be no current flowing down. Because I have no vertical component coming into it, I can't have any vertical component coming out of it. But because I do have a vertical component here, this can be verified with just a simple ammeter, then evidence that it is not a vector. All right, so let's pick the easiest one, because I've got two currents flowing across the 3 ohm and the 4 ohm resistors. So let's just do the 6 ohm and the 5 ohm. The 6 ohm resistor, the only thing I have going across that is C, which we've figured out is 86 107ths, which presumably is some decimal. So this would be 86 over 107 amperes, and that is flowing, that's the 6, to the right. The 5 ohm resistor has only one current flowing across it, that's B. And it is down, so this is 146 or 107 amperes going downwards. All right, across R4, I had two currents. I've got B and C both flowing across it in the same direction, so I just add them. Let's see, for the 4, that's going to the right. So 2, 3, 232. And across the 3 ohm resistor, I have my two currents. I have both going to the left, so I would just add them. So 232 over 107 amperes going to the left. And it makes sense. The current flowing across R3 has to be the same current flowing across R4. I have a junction in between. There's nowhere for it to split. And then this last bit is what is the potential difference across the 5 ohm resistor. Well, I know potential difference across a resistor is the current times the resistance. I know the current, that's 146/107. I know the resistance, it's 5. So if I multiply 5 times that, zero, 3, I think 730 volts. If I go in the direction of the current, so if I'm going down, do I gain potential or lose potential across a resistor? I've established that the current is flowing this way, so if I go with the current, am I gaining or losing potential?
Losing.
Yes. And so if I want to go in that direction, I need the minus sign there. Any of these directions, if I flipped them, I would just add a negative sign to the magnitude. So for example, this one could have also been 730/107 volts positive upward. Either of these are acceptable answers. Questions? Does the clock match this one? In all its glory. I feel like we should do this problem again. Except the other technique. Because I feel like we just went through this, and if this works for everyone, it'll work for everyone, but, you know, I want people to get a better feel for which technique works better for you as an individual. I need to get rid of stuff over here. Good enough. Let's see, lasso it. One current per path. I have 3 paths. I have 2 junctions and I have 3 ways of getting from one to the other. So what I'm gonna do is let's first highlight. I have a junction here and a junction here. How we choose our currents is completely arbitrary. I'm going to just go from the bottom to the top. Why not? I'm going to call this current B. Let's actually pick different letters. So current D. And then this way, current E. And then this way, F. Now the reason I'm picking different letters is that I've done this before where I pick the same letters, you know, B and C show up again, and I'll have a moment where I'm going, wait a second, that's not the value we had for B before. That's because the B's represent something different. So, I think, for my mind, just different letters. I have 3 unknowns. How many equations do I need? Say it out loud.
3.
Yeah, all right. Let's do it. We now need our 3 equations. One of the equations will be the junction rule. 2 of the equations will be voltage rules. So what's the junction equation? It's the old current in equals current out. Pick a junction, any junction.
I might be confused. Could you elaborate?
All right, so the question, when you're doing the junction rule, pick a junction, it doesn't matter which one. What's it?
Bottom junction?
Bottom, all right. What are the currents flowing into it? Stephanie? None. All right, so that's the current flowing in, and the current flowing out.
D, E, and F.
There's the junction. If we picked the top one and did current in equals current out, then it would be D plus E plus F equals 0. Now, I will tell you, if I have 3 numbers, none of which are 0, and the sum is 0, I know at least one of these is negative. I know that's earth-shattering. Now, voltage rules. We pick a point, we go in a loop, we end up back where we started, sum is 0.